Hi, this is Mike, and today we're going to take a look at another Autodesk Fusion 360 simulation validation model. This is the third one that I am recording today. It's going to be rather simple geometry. It's a thick cylindrical disc under uniform radial pressure. So let's go ahead and take a look at what we have for the description of it here. And so this example comes from Rourke and Young, formulas for stress and strain, as have the other ones. Reference page 504, table 32, case 1A. Again, it's a thick-walled cylinder disc with uniform internal pressure. The pressure is defined for us as 1,000 psi. The OD on this geometry is going to be 12 inch. The ID is going to be 6 inch. The height of the geometry is 3 inches, and then the material properties given to us are a modulus of 30E6 and Poisson's ratio of 0.3. Our theoretical deflections, you can see there is 1.967, e to the minus 4, and then the theoretical max hoop stress is 1667. So, like always, we'll run the simulation, then we can plug our values in that we get with Fusion 360 and see what sort of difference we have. This one, I'm going to start it from scratch inside the Fusion environment. Normally I have the model prepared, but again, it's just such a simple geometry. So if you missed that step, many of you are probably already familiar with how to draw or model within Autodesk Fusion 360, and now you're curious about some simulation. But just in case you're completely new, Fusion has a number of different environments, and we'll get into simulation here shortly. But starting in the design environment, I'm going to say that I want to create a sketch, and I'm just going to select a plane that I want to sketch on. And then from there, I can go with my sketch tools. I have circles and rectangles, lines, etc. So we're just going to start with a circle, and we'll drag that out a little bit. And then, of course, we need an ID and an OD. And so I'm just going to place two circles there and then grab the dimension tool. And let's go ahead and start the dimension. The ID, again, was 6 inches. So I'll go ahead and define that. And then the OD was a 12-inch one, so we'll define that. And then at that point, we can go ahead and say that we want to finish this sketch. And then from our solid tools, we can say that we want to extrude, select the annular ring, and the height of this is going to be 3 inches. So I'll just type in 3, say OK. All right, so that is the geometry. And I realized that in the other examples that I've done, that I've always used symmetry. And we could use symmetry for this. As we add our internal pressure here and expand this cylinder or ring, at any point, around the circumference of it, my result should be the same. So what I get over here should be the same type of result that I get on this side, or over here should be the same as here. So certainly we could just model 1/2 of this, or we could model a quarter and add our symmetry constraints. I've done those types of things in the prior two models. What I'm going to do with this one is we'll just model the full thing because it does present some of its own unique challenges. So for instance, we want to add the pressure in here and allow the whole thing to radially expand outwards, but we still need to keep the model statically stable. And so what we can do for that, what we do in those situations a lot of times, would be to split the geometry and add constraints that won't negatively impact our results. So let me rotate this geometry around so I'm looking at the bottom side of it, and we'll start a sketch on that face. So I'm just going to select my sketch tool, select the bottom face of my geometry, maybe move the mini axis around a little bit here. All right, so what I want to do is I'm going to create a line, from, let's say, if this were the face of a clock, from 12 to 6, and we'll split that geometry so that I have an edge here and an edge here, and then we'll do the same thing from the 9 o'clock to the 3 o'clock position. So let me go ahead, and start with those sketches. There we go. I'm wondering if I can do this all in one shot. So let's try that and we'll see how that goes. So I'm just making the pattern there of crossing lines. And then from there, I'm going to go to the modify tool. I'm not 100% sure that I can select all that sketch. I might only be able to select one sketch line at a time for this, but we'll see. So let's go to modify, and what I'm looking for is the split face tool right there. And we're going to select faces to split. That would be, the circular face there. And then we need to select our splitting tool, hoping that it lets me select the whole sketch. It doesn't. It looks like it just allows me to select a line. That's okay. Let's go ahead and say okay. So what we can see there is it has now split that surface into two. And I'm going to stop there. We do need to add the other one in, or the other splits, but I'm going to talk about this for just a moment. So what is the benefit of this? Imagine we're going to add our pressure in, referencing my mini axis, right? So X is in the vertical direction here, and Z is left and right. So X is this way. As we add internal pressure radially outward, the nodes, if you will, when we mesh this, there's a little point or vertex that I can highlight. As we add uniform internal pressure, this little dot here, this vertex, this point on our geometry should move because it's in the 12 o'clock position, should move purely along that axis, right? So what that means is I can use this edge now for constraints and constrain any nodes along that edge and keep them from moving in any direction or apply a constraint that stops any translation or rotation except for translation in the x direction. So for instance, on this edge, we can apply a TZ and a TY constraint, right? Because these nodes or what will be the mesh along this edge should not move in the Z direction or in the Y direction, which would be my in and out of screen at this point. So you can imagine the same thing. Once we split a line here from the 3 to 9 position, anything along that edge when we add the uniform pressure should just move, anything on the right-hand side of the model here should just expand outward along the Z-axis, but I should see no X movement. And then anything over here should move out in the Z-axis, but not in the X. So that, those split lines will allow me to add the constraints in a little bit later that we want to have so we can do a full model and not add in, as I say, any constraints that would negatively impact the results, right? So there we go. So there's the quarters there. I need to do the same thing over here. Just do a sketch over here. I haven't done very much formal learning on Fusion, the design environment. I'm sure there are many people out there who can sketch a lot faster and better, maybe provide some input about how I could have done this in a simpler way. My focus, my passion is really with simulation, and I learn enough modeling either in Fusion or Inventor or whatever CAD package may be the case, just to be able to get by, to be able to create the models that I want to create to do the simulation. So there are my 4 splits. That will be enough for us to constrain the geometry. Let me go ahead and save this. So I'm going to do a save, and I'll call this validation 3. For instance, and then we're going to go ahead into the simulation environment. From the design pull down menu, I am going to go into simulation. And as we go into simulation, again, there's my different analyses types. So I'm going to start with a static stress here. This one is a static stress. Okay, and then we need to define the basic things that we need in an analysis. And that would be the materials, right there, the constraints, the loads, and the mesh. We don't have to worry about contacts. Those would come in with an assembly. So the material is first. Let's go ahead into the materials here. And again, they gave us a 30E6 and a Poisson's ratio of 0.3. It has a steel material associated with it. Let's see what that is. So it's just about there. It's 3.04E7 and a Poisson's of 0.3. I think if you use that material, that would probably be close enough, or you can uh, go into the study materials here and find something that's maybe even closer. Let's take a look at just off the top of my head. Let's take a quick look at ASTM A36. And let's go back to study materials. I already have one set up, a one that I defined. So that's 29E7 or 2.9E7 and zero point 0.3. Again, kind of close enough if you wanted to use that if you're setting it up on your own. I've already defined my own, put it in my own library. So I'm going to go ahead and grab that. So I put it in a library called Fusion Validation Library. And then the material, I've saved it, from my last validation example, which was validation 2, and then I named it with what I defined the modulus and the Poissons as. So that way I know exactly what I'm getting here. Click off of that and say properties. There you can see the Young's modulus is 3E7 and Poisson's is 0.3. Okay. All right. If you have questions about that, how did I create my own material? What you can do from the upper right hand corner, there's a question mark right there, and there's learning and documentation, just FYI, product documentation. And then we could get in here and we could say material, for instance, and there's override materials, material and appearances, modify physical materials. There's got to be a select materials and a generative study. So maybe that isn't the best way. I wonder if I do custom material, or maybe user-defined material might be even better. There we go. Add new or custom simulation materials. So custom material, and then the topic is add new or custom simulation materials. And you can see that there are all the steps there that will guide you right through it. So if you need to do that. But again, you could select something that's close, and I'm sure you'd come out with very similar results. The next thing are the constraints. So let's rotate the model around again, back to this backside. And I'm going to select that edge because we can select vertices or a vertex of our geometry. We can select surfaces for constraints, and we can select edges. So I'm going to select that edge right there and that edge right there. And again, anything along this line should move purely in what? In this case, the z direction, the way I have the model oriented now. So I'm going to let z free, which then constrains tx and ty. So that's 2 out of the 3 constraints that I need to keep a model statically stable, right? Somehow in a linear static stress analysis in general, you should account for all 3 degrees of freedom ideally, so that the model doesn't drift off into space in the x direction or drift off into space in the y direction, etc. There are provisions in the software that can allow for such a thing, or help to stabilize the model in such a way, but I prefer to add in constraints similar to this. Let's go ahead and say okay. We're going to add additional constraints. That would be this edge right there and that edge right there. In this case, these ones I want to be able to move purely in the x direction, so I'm going to uncheck ux. So there's my y and z. So y is applied to both of these. So that's basically the bottom surface of this geometry, right? So the bottom surface is if it's sitting on a table or something like that. Those nodes are not going to move vertically. Anything above that, though, the model could grow or shrink along the y-axis, just not the very bottom edges there that I selected. And then, the way that I applied it, this one's constraining uz, or these 2 segments are constraining z, this one, and then these 2 are constraining also x. So with those constraints, I have accounted for all degrees of freedom. So we'll say OK to that. What else do we need to have? We have our materials, we have our constraints, loads, something else we always need on the model, and the load definition was 1,000 psi pressure. So nice and simple load, internal there, and pointing radially outward. We're just going to make it 1,000 psi. There we go. And then again, contacts are for assemblies. We don't have to worry about that. I do want to have a mesh. So I'm going to turn on the visibility of the mesh, or just click that button and it says, hey, you haven't computed a mesh yet. Would you like to do that? And I'm going to say yes. And we'll see what that gives us. I might want a finer mesh. It's a little bit coarse. So I'm going to go over here to the browser and let's edit that. I would like at least maybe, I don't know, I'm just ballparking here based on experience. I would like maybe 4 elements in the height, roughly, just as a starting point. We can always look at our results and change it. And that's another good thing. If you have no idea what the results of your analysis should be, it's always wise to run a couple different mesh sizes so that those different mesh sizes, hopefully you see that they all have very similar results. If the results are changing drastically with you only changing the mesh size, then you know that you haven't necessarily come across the proper mesh size for that geometry yet. I'm going to use an absolute mesh size. It's 3 inches, right? So half of that would be 1.5. Half of that would be 0.75. 0.75. I said that like it was a question. It's the end of the week. Maybe I'm getting a little tired. I don't know. All right, let's start with that. And because we happen to know our displacements in this case, we can take a look at the displacements. And if our results are far off, we can always take a look at, hey, let's go ahead and try a finer mesh and see how that improves our results. Since I brought it up earlier, let me go under the Manage pull-down menu. And I'm going to go into Settings here. Manage and settings, since I mentioned it a little bit earlier. So there is an option in here. It says remove rigid body modes. I don't need that because, again, my combination of constraints in this model fully account for X, Y, and Z. But sometimes you don't necessarily have that. Could you imagine if we had a model of a soccer ball, right? And you're inflating this soccer ball, how would you constrain that, right? I would do a similar thing globally on the model. If you picture it like a globe at the very top and the very bottom, those points are just going to move along the vertical axis, and then you pick along the sides, I guess west and negative west, or again, you could use the face of a clock there and say it's 12, 3, 6, and 9 around the circumference of the ball. But sometimes people don't want to have to go, through that kind of motion, so you can say remove rigid body modes. And presuming that the model is relatively stable enough, just given the constraints or loads that you have on it, that should take care of it or help stabilize it. But yeah, it is there if you're wondering if you've used other programs that have that capability. Let's go ahead and solve this. I'm going to say solve. And again, we can choose an on the cloud solve or say locally. Let's do one of each. Let's say on the cloud first. And why not use some cloud credits here. And just in case this is the first one of these videos you stumbled across, just to see the experience. So it sends it to the cloud and it begins the solving. And then, as soon as it finds a machine and can start that processing, and it's done, it sends it back. So everything is complete at this point. That was all real time. Let me close that and close that. So it's going to show me the safety factor by default, but what we want to look at are the displacements. So there's my displacements, and that looks pretty good. Let's take a look at in a specific direction. Let me look at my mini axis here. So I want to get just the radial displacement. So if I do say, I guess I could do either X or Z. So my X max is 1.959. And let's take a look at, I should see something very similar for Z, just at 90 degrees from there. And there we go, 1.96. Okay, so let's plug that in. There we go. That's E minus 4, so 0.001963. Hit enter. So about 0.2% different from the book value. And the next thing that we need to do is take a look at the stress. And by the way, that is a hoop stress result that it's looking for. So when I go over here and I say I want to look at stress, by default, it's going to give us a von Mises. We want a hoop. So again, we're going to do either normal X or normal Y. So if I do the normal X direction, 1669 there. And normal Z, 1689. That one is a little bit higher. So let's take a look at, and again, that would be variability due to my mesh. So I could refine the mesh and clean that up a little bit. But let's take a look at those values. So 1669, of course, is going to be really close. 1669, I get a 0.1% difference. We'll use the larger value because that's the greatest error in my model. 1689, so let's plug that in. 1689, and there we go. So that's a 1.3% difference. Still something that I could live with. And that's a question that people give me from time to time, like what is a good enough percentage? And it all kind of depends, right? What are you going for? Are you just trying to make sure that this design is safe? In that case, this is a steel material. You could have used A36. The yield of that material would be 36,000 psi. Our hoop stress here is only 1689, so it's really low. On the other hand, if you were up against that yield stress and you wanted to be really precise, then yeah, I'd probably interrogate this a little bit more. But you don't want to like go crazy trying to zero in a stress. I think I'm not I'm a simulation specialist, so I teach a lot of simulation and help people with their simulation, but I'm not in the business of having to create products personally and be responsible for the what I want to say, the durability of those products, or ensuring that the stresses are 100% correct. But the people that do that and use finite element analysis to validate it, I think after you run 3 different mesh sizes at least, and you find that the stresses are converged, that is, those 3 different mesh results are all fine enough, the mesh is fine enough that it's giving you similar results. I think that if you had, results that were within, say, 5% of maybe what a hand calculation gives you, I think that's probably a good, pretty good ballpark right there, because, you don't want to have to spend too much time or invest too much time in the analysis just for those tiny amounts of increase in accuracy, when we're already, again, we're even at the worst of the 2 values, at this one, we're still 1.3% off from the hand calculation, which is really close. So I hope you enjoyed that example. If you have any questions, pop them down in the comments, and I'm trying to look. To be honest, not daily, but I try at least once a week to take a look and see if there's anything I can help with. So thanks for watching. Have a great day. Take care.